Hello, everyone, and welcome to Section 2 of the Abstract Modern Algebra Lecture Series. This section is only going to have one lecture video. It's not going to be split up into parts because we should be able to cover everything in one video. So in Section 2, we are going to go over orders, subgroups, and centers. So, this section focuses on finite groups. And finite groups are groups with finitely many elements. All right, so first thing we will take a look at is orders. So we have two orders to consider with groups, and those are orders of a group and orders of elements in a group. And the notation that's used to describe orders is basically closed brackets. And if you remember, this is similar to cardinality. So, an example, for the group Z8, or a group of integers from 1 to 8 under addition, we have 0, 1, 2, 3, 4, 5, 6, 7. So then the order of Z8 is 8. All right, and then we have order of an element. Oops. There we go. And an order of an element is the smallest positive integer, often denoted by n, such that an element raised to the nth power equals the identity element. And we represent an element with G for this definition. An element of a group. If we have an addition operation, we would say the smallest integer n where ng equals 0. All right, so let's look at an example. Let's look at the group U of 8. If you remember, that's just the integers prime to 8. So since 1 is the identity and 1 raised to the n equals e, then the order of 1 is 1. And for 3, we have 3 raised to the 1 equals 3. It's logically equivalent to 3 modulus 8. 3 squared equals 9, which is logically equivalent to 1 mod 8, which is equal to the identity element. So the order of 3 would be 2, because we have to raise 3 to the power of 2 to get the identity element. And then let's look at 5. We have 5 raised to the 1 is 5, which is logically equivalent to 5 modulus 8. But then 5 squared is 25, which is logically equivalent to 1 modulus 8, which is the identity element. So the order of 5 would be 2. And then for 7, 7 raised to the 1 is 7, or 7 modulus 8. Then 7 squared is 49, which is 1 modulus 8, which is the identity element. So the order of 7 is 2. All right, so that's pretty much all there is to look at for orders of groups and elements. So now we will move on to our next topic, which is we'll change colors here. It's going to be subgroups. So let's look at the definition of a subgroup. So a subgroup is a subset of a group, let's call it G, that is itself a group. Or when we say it's a group itself, basically it satisfies the group properties. And if you remember from section 1, the group properties were closure under its operation, associativity, it has an identity, and it has inverses for all of its elements. So a notation for a subgroup is similar to the less than or equal to symbol. So we have 3 different tests that can be applied to show a subset of a group is a group. And these tests are nice because they are simpler to use, because you don't have to check all the group properties with these tests. So they're simpler to use than verifying all the group properties. So let's take a look at these tests. So the first one is the one-step subgroup test. So here is the theorem for this test. So we're going to let G be a group and H a non-empty subset of G. So if A B inverse is in H whenever A and B are in H, then H is a subgroup of G. And if we have an addition operation, this would be if A minus B is in H whenever A and B are in H, then H is a subgroup of G. All right, so of course this is a great theorem, but let's look into it a little more in depth and look at the proof of this subgroup test. So we're going to let G be a group and H be a subset of G. So since H is a subset of G, H shares the operation of G and is associative. So now let's let X be an element of H. Since H is non-empty, let's suppose that A equals X and B equals X. So then the identity element equals X composed with X inverse, which equals to A B inverse. So A composed with B inverse is an element of H. Now let's suppose that A equals the identity element and B equals X. So then AB inverse equals the identity element inverse of X equals the inverse of X. So the inverse of X is an element of H whenever X is an element of H. And now the last thing to look at in this proof is, let's suppose A equals X and B equals the inverse of Y. So then XY equals XY inverse, or the inverse of Y inverse, which equals AB inverse, where AB inverse is an element of H. So therefore, H is a subgroup of G. So by going through this proof and, oops, lost my square. So by writing out this proof and leaving us to only have to focus for this test on if the composition of an element and the inverse of another element is in the subset of our group, then by itself it is a subgroup of G, or of the group G, just by doing this test. So that is the one-step subgroup test. Now let's look at our second test, and that is the two-step subgroup test. So the theorem for this is, let G be a group and H be a non-empty subset of G. So if AB is in H whenever A and B are in H, and the inverse of A is in H whenever A is in H, then H is a subgroup of G. So let's take a look at the proof. And compared to the last proof, this is a shorter proof. So let's let G be a group and H be a subset of G. So then H is non-empty associative closed and every element of H has an inverse. So now let's suppose A is an element of H. So then A inverse is an element of H. So hence A inverse equals the identity element. So the identity element is an element of H. So therefore, H is a subgroup of G. Yep, pretty straightforward proof. And this gives us our second subgroup test that we can use. Now, of course, these tests you may not be able to use them for every group or subgroup. It would just depend on what subgroup or what subset of a group you're trying to determine whether it's a group or not, and which one you think would be easier to or more logical to use. All right, so we have one more subgroup test to look at. So our third subgroup test is a finite subgroup test. So the theorem for this is let H be a non-empty subset of a group G if H is closed under the operation of G, then H is a subgroup of G. So let's look at the proof for this test. So let G be a finite group and H be a subset of G. So now let's let A be an element of H. Then A inverse is an element of H if A equals the identity element and A inverse equals A, we are done. So let's see if we reach that conclusion. So let's suppose A does not equal the identity element. So let's consider the sequence A squared, etc. So by closure, this sequence is an element of H. So since H is finite, not all of these are distinct. So now let's suppose AI equals AJ, where I is greater than J, and I and J are integers. So then A raised to the I minus J equals the identity element, and I minus J is greater than 1, since we are supposing that A does not equal the identity element. So thus, A raised to the I minus J minus 1 equals A inverse. However, I minus J minus 1 is greater than 0. This implies that A raised to the I minus J minus 1 is greater than, is an element of H. And since we have found that, we are done. And this proof is complete. So this subgroup test on the when you look at this proof might seem a little complicated to understand at first, but we are actually going to look at an example of using one of these subgroup tests, one of these three, so to where you might be able to see an application of these tests. So now we will look at an example of deducing a subgroup. So this is the theorem we will be looking at for this example. Let G be a group and A be any element of G. So then this group of A is a subgroup of G. And we will look at the proof of this, and then I will explain what this subset, which of course when we do the proof you will see it'll be a subgroup, what it's going to be defined as, which is why I just called it a set of A for this theorem, because we haven't technically deduced or defined what this is yet. So let's look at our proof strategy, and here we will figure out what subgroup test we will use. So we are wanting to prove that the group A, or for the group G, that for an element A, that this group, this subset A is a subgroup of G? Well, when we look at these three subgroup tests and what we need to figure out, the simplest test that would probably logically make sense would be to do the one-step subgroup test, and look at where for two elements inside the subset, that if we have the one element composed with the inverse of the other, then it is a subgroup. So this is what we will define in our proof strategy, or describe in our proof strategy. We will use the one-step subgroup test, or as we defined it in this lecture, subgroup test 1, to show that for elements A, N, A, M, that A, N minus M is an element of A, which shows that this subset A is a subgroup of G. And A raised to the N minus M is the same as A times, or A composed with the inverse of B. We're just defining elements as A raised to the power of some integer for our elements of this subset. All right, so let's take a look at our proof for this. So let's let G be a group, A be an element of G, and this set of A be a subset of G. Let's let A be an element of our set A. So then our set of A is non-empty. So now suppose that A raised to the N, A raised to the M are elements of the set of A. So then A raised to the N composed with the inverse of A to the M is equal to A N minus M. So A N minus M is an element of A. So therefore, this set of A is a subgroup of G as desired. So now, for this set of A that we have just proven that is a subgroup of a group G, what are we going to call this? What is its application? Try Still haven't got the hang of drawing decent looking squares at the end of these proofs. I feel like I'm getting better. So this subgroup is called a cyclic group. And this is important to remember because this will be a main focus of section 3 when we get there. And we will look at it more in the next section, section 3. All right, let's change topics and look at our last topic for this section. Let's see, which color are we going to choose? Let's go with orange. All right, now we will look at centers and centralizers. All right, so a center. The definition of a center is the center, and it's notated as ZG of a group G is the subset of all elements in G that commute with every element in G. So this is kind of a shorthand definition for this. C of G equals the set of elements of a group G such that these elements times X equals X times the elements for all X in G. And a fun little fact about where the ZG comes from, this comes from the German word for center, Zentrum. It was coined by J.A. de Segure, if I'm pronouncing that right, in 1904. So let's look at the theorem and proof for the center of a group. So the center of a group G is a subgroup of G. Or excuse me, this is a theorem that comes from the definition of centers, and we're going to prove that it's a subgroup. So let's take a look at what our proof strategy will be. So we will use the two-step subgroup test, or as we defined it in this lecture, subgroup test 2 to show that AB is an element of the center of our group whenever A and B are elements of the center of the group, and the inverse of the elements are elements of the center whenever our elements are present in our center. So now we will be applying our second subgroup test. That's good enough, I guess. All right, so let's write out our proof. So let's let G be a group. So since the center of G is a subset of G, the identity element is an element of the center, and the center of the group is non-empty. So now let's suppose A and B are elements of the center. So then ABX equals ABX equals AXB equals AXB equals XAB equals X times AB for all X that are elements of the group. So therefore, AB is an element of the center of the group. Now let's suppose A is an element of the center of the group. So then we have XA equals AX for all X that are elements of the group. So A inverse XA, A inverse equals A inverse. I had this mixed up. XA, A inverse. And this implies that A inverse A, XA inverse equals A inverse X A inverse, which implies the identity in XA inverse equals A inverse X identity, which implies a negative 1 equals a negative 1x. So, hence, a negative 1 is an element of the center of the group whenever a is an element of the center of the group. So, therefore, the center of the group is a subgroup of G. Let me write in as desired. There we go. All right. So that's pretty much all there is to look at for centers. Now let's look at centralizers. So the definition of a centralizer let's let A be a fixed element of a group G, and the centralizer of G, denoted by CA, is the set of all elements in G that commute with A. And to write out a shorthand way of doing this, centralizer of A is equal to the set of group elements where GA equals AG. So let's look at a theorem for centralizers, and it's pretty similar to the theorem that we had for centers, that for each A in a group G, the centralizer of A is a subgroup of G. And our proof strategy is going to be a very similar proof to our last proof will be used. So we'll use the two-step subgroup test again and follow pretty much the same steps that we did for our last proof. So let's start writing our proof. So let G be a group and A be a fixed element of G. So since centralizer of A is a subset of G, the identity element is an element of our centralizer, and our centralizer is non-empty. And what I'm going to do for the remainder of our proof, we can just copy what we wrote here, and we will just change up our variables and terms. And we will put it down here. There we go. Let's slide it over here. Come over this way a little bit. All right, that's good. So what we are going to change is, since our centralizer is defined by an element A, we won't use the element A. Instead, we use the elements B and C. This will be our centralizer. And this will be BC. 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 BC for all x. That's good. And therefore, BC is an element of our centralizer. And then we'll suppose that B is an element of our centralizer. And then change these to B. So once we get all these changed, we will have our proof for this. This is our centralizer. Man, there we go. And therefore, our centralizer subgroup of G. So we basically did the same thing that we did for proving that the center was a subgroup of our group. We just defined two elements and proved that there is closure and that there are inverses for every element. All right, that is it for section 2 of the Abstract Modern Algebra lectures. Thank you guys so much for watching, and I will see you guys in the examples to finish up this section.